Standard temperature and pressure is abbreviated STP, and it's defined as 1 atmosphere of pressure and 0 degrees Celsius. So you should know what standard temperature and standard pressure are. So this standard pressure, that's regular atmospheric pressure. That doesn't look like regular. Whoops. Regular atmospheric pressure. Would that be easy to achieve in a chemical experiment? Just normal pressure? Yeah. If the thing is open to the atmosphere, it's 1 atmosphere of pressure. Standard temperature is the freezing point of water. That's also an easy temperature to obtain, because if you want something to be at 0 degrees Celsius, you just submerge it in an ice water bath. Because ice and water together, always 0 degrees Celsius. So that's what helps me to remember what these numbers are. 1 atmosphere is 760 torr. That's that relationship we should remember. And 0 degrees Celsius is 273. See there, they're being sloppy and leaving out the 0.15, 273 Kelvin. STP is useful for making comparisons between gases, because as you've seen, there's like a bunch of variables here. And so how do you compare this gas to this other gas when all these other things are different? So we choose to compare them at STP. So we can calculate the volume of 1 mole of gas at STP. That's called the molar volume. Molar mass was the mass of a mole, right? Molar volume is the volume of 1 mole. So volume of 1 mole of gas at STP, so 273 Kelvin and pressure of 1 atmosphere. Let's calculate what that would be. Well, the volume is going to be nRT over P. N is 1 mole. R is 0.08206. Liter atmospheres per mole Kelvin. Temperature is 273 Kelvin, not 0 degrees Celsius. If we stuck 0 in there, then our volume would be 0, and that's not possible. And 1 atmosphere. So the moles cancel, the atmospheres cancel, the kelvins cancel. .4 liters. It's often expressed with 3 significant figures, although it could be done more precisely. So 1 mole of gas at STP has a volume of 22.4 liters. Now, just for, how big is 22.4 liters? Well, it's like 11 bottles of soda, right? But that's hard to imagine. It's a cube about this big. So like a fairly good sized packing moving box, right? That's about the size of 1 mole of gas at 0 degrees Celsius and normal atmospheric pressure. So this number makes a great conversion factor between moles and volume of a gas at STP. Any questions? This value is true for any gas at STP. A mole, remember, is 6.022 times 10 to the 23rd particles, molecules or atoms of the gas. So this many molecules of any gas at STP occupy the same volume. This is kind of strange. That doesn't happen with solids and liquids. So 1 mole of different gases going to have the same volume. They're going to have different masses, though, because the individual particles have a different mass, they're just occupying the same volume. Not because all the particles are the same size, but because a gas is mostly empty space. So this is a very useful conversion factor, 22.4 liters per mole. There's this an illustration to help us think about this. So here's a mole of helium at STP, occupies 22.4 liters. A mole of xenon, 22.4 liters. A mole of methane, 22.4 liters. Do those balloons have the same mass? No, they don't. Because the individual particles in here have different masses. We have the same number of particles in each balloon. They're occupying the same volume. But what does a mole of helium weigh? 4 grams? Right? And xenon? About 131 grams. And methane? About 16 grams. So these balloons will have very different masses, but the same number of particles and the same volume. Any questions? So if those gases had the same volume but different masses, that means that their densities are different. Density is the ratio of mass to volume. So we learned earlier that density equals the mass of an object divided by its volume, right? For solids and liquids, that was usually grams per milliliter, grams per cubic centimeter. The density of a gas is much less, and so we usually use the unit grams per liter to make the number more reasonable. We can calculate the density of a gas. You can take the density, you can say that the density equals the molar mass of a gas divided by the molar volume. That's nice, but I think it's better to just stick with density as mass over volume and think about it. This is one of those cases where if I ask you to calculate the density of helium at STP, I'm not going to give you an amount of gas, because it's going to be the same no matter how much gas you have. So you have to choose. Choose an amount. So just choose 1 mole, right? So we're just going to choose 1 mole. And that's where this comes from. But over here, we're going to find the density of helium. So the density of helium is going to equal the mass of helium divided by the volume. We're choosing 1 mole. What's the mass of 1 mole of helium? 4.003, right? We'll be a little more precise here. What's the volume of 1 mole of helium at STP? 22.4 liters. So 4.003 divided by 22.4. .0179 grams per liter for helium. Let's do nitrogen. So for nitrogen, we're also going to choose 1 mole. What's the mass of 1 mole of nitrogen? 1 mole of nitrogen atoms is 14 grams. Is nitrogen a diatomic element? Yeah, it is. So nitrogen is actually N2. So then the mass of 1 mole of molecules is 28.02 grams. It's the number of particles. And the volume is also 22.4 liters because we are at STP. So 1.25 grams per liter. So helium is less dense than nitrogen. That's why helium balloons float in air. Air is mostly nitrogen, and the helium is less dense, and so a balloon with helium in it will float. Any questions? The gas density is directly proportional to molar mass, and your book goes through this and shows you that you could do it this way. The density is equal to the pressure times the molar mass divided by RT. In my opinion, that's just another equation to remember, and so I'd prefer to just stick with density as mass over volume, choose a mole, and go from there. So that's what I'm going to demonstrate for you. Calculate the density of xenon gas at a pressure of 742 millimeters of mercury and a temperature of 45 degrees Celsius. This is not at STP, so we can't use 22.4. It says calculate the density. So I said, well, density is the mass divided by the volume. So I'm going to choose 1 mole because that makes all the calculations easier. So what I need is the mass of 1 mole and the volume of 1 mole. Well, the mass of 1 mole is easy. Xenon is a noble gas, it's not diatomic. So we just look at the periodic table and we see that 1 mole weighs 131.3 grams. That's the mass of 1 mole of xenon gas. How do I find the volume? Ideal gas law. The volume is equal to N RT over P. And I decided that N was 1 mole. And then I've got R. I need my temperature. So they gave me a temperature of 45 degrees Celsius. What do I need to do to that? I need to put it into Kelvin. So I'm going to be sloppy and just do it that way. 9 and check me on my math there. I did that in my head. 319 Kelvin. And then I'm going to divide by the pressure. They gave me millimeters of mercury. Pressure 742 millimeters of mercury. So I convert that. 1 atmosphere is 760 millimeters of mercury. Sometimes when students do this calculation, they get 1 millimeter of mercury is equal to 760 atmospheres. No. To help avoid that, think back to that original mercury barometer. They were measuring atmospheric pressure, which is 1 atmosphere, right? And they're measuring how tall the column of mercury was. It's not 760 atmospheres, it's 1 atmosphere in 760 millimeters of mercury. So I've got 742 divided by 760. (976.31 atmospheres). So that goes in the denominator. I check out my units. Moles cancel atmospheres, kelvins. I'm left with liters, which is what I wanted. So I've got the ideal gas constant times 319 divided by 0.97631. It's 26.812 liters. That's the volume of 1 mole of xenon under these conditions. coming up with 4.90 grams per liter. So you can use the equation that your book gives you. You're still going to have to convert the temperature and the pressure, and it's just another equation to remember. So do what makes sense for you. We can also use the ideal gas law to calculate the molar mass of a gas. And we're going to do this in lab, I think, on Wednesday. You can take a volatile liquid. Volatile means that it evaporates easily, has a low boiling point. We can heat a sample of this and turn it into a gas. If we know the mass of it, we can measure the temperature, the pressure, and the volume, and then we can calculate the moles using the ideal gas law. Come on, pointer. Calculate the moles using the ideal gas law because we measured temperature, pressure, and volume. So we can find the moles, and then if we have the mass, molar mass is the mass of something divided by how many moles are in it. So you take the mass of the gas divided by the number of moles. You can calculate the molar mass. Let's do an example. Sample of gas has a mass of 827 milligrams. Its volume is 0.270 liters at a temperature of 88 degrees Celsius and a pressure of 975 millimeters of mercury. Find its molar mass. So we can write down those numbers. Let's do that. Mass of, so the mass equals 827 milligrams. The volume is 0.270 liters. The temperature is 88 degrees Celsius. And the pressure is 975 millimeters of mercury. So I've harvested the numbers. Those are the things I'm going to start with, right? And then I have to think about, well, what am I trying to find? I'm trying to find the molar mass. So then I ask myself, well, what is molar mass? What are the units of molar mass? Grams per mole, right? So molar mass is equal to the mass in grams divided by the moles. So I need to find the mass of this sample and its volume. Well, they gave me the mass, but it's in milligrams. Can we convert that to grams? Sure we can. So I'm going to put milligrams in the bottom and grams on top, and then I ask myself, what does milli mean? Milli means 10 to the minus 3. So I've got 1 milligram on the bottom, and I have 1 times 10 to the minus 3 on top. So this is equal to 0.827 grams. So 0.827 grams. Now I'm looking for the number of moles. So that's going to be the ideal gas law. So PV equals nRT. I need N by itself. So I'm going to divide by RT on both sides. The R's cancel, the T's cancel. N is equal to PV over RT. So my pressure was given in millimeters of mercury. Does that work? No, it doesn't. 1 atmosphere per 760 millimeters of mercury. Now, what you can do, and if this works for you, it can save a little bit of time. You can write the 795 divided by 760, and that's in atmospheres. And you can kind of do the math within the problem. But I'm not going to do it that way. We're going to actually just do the calculation and write it down. 975 divided by 760, 1.2828 atmospheres. 1.2828 atmospheres. My volume is in liters, and that's what I need, so that was great. R, 0.08206 liter atmospheres per mole Kelvin, and then the temperature. I have to put that into Kelvin. (361 Kelvin). I check my units. I'm left with 1 over mole, which is the same as mole. Now, when you do this on your calculator, you need to be careful, because what your eye probably sees is this number times this number divided by this number times this number. And if that's what you tell your calculator, you're going to get the wrong answer. You could use parentheses. So if you use parentheses, let's get something we could see. I'm going to use parentheses down here. If I want to multiply, I have to put parentheses around the bottom. So that works. The other thing, well, there's a couple other things you can do. You can think of this as two fractions that are multiplied. So it's this divided by this times this divided by that. That's going to work. Or what I do is I take this times this divided by this, and then I say, well, that whole mess is still divided by this. So there's 3 different ways to think about it. Make sure that you punch it in on your calculator and you come up with the same number as the rest of us. So 1.2828 times 0.27 divided by 0.08206 divided by 361, 0.01169. Anybody else get that number? So that's the moles. That's a really small number of moles. It's okay. We've got a small mass of gas. So I'm going to plug this into my equation that I've got going up here, 0.011691 moles. So I've got 0.827 divided by 0.011691. Oops, got an extra digit in there. And I'm getting 70.738. Units are grams per mole. That would round to 70.7 grams per mole. Yeah.
So molar mass always indicated by grams over moles, or can we say moles over grams?
Molar mass is always grams over moles. Or you could separate them and say 1 mole is equal to this many grams. But we never say 1 gram is equal to this many moles. Is that a reasonable molar mass? Well, what's reasonable? What is a possible molar mass? Or maybe what's an impossible molar mass? Could I have a molar mass that's 0.7 grams per mole? What's the smallest element? 1 gram per mole. That's hydrogen atoms. And even that as a gas is 2 grams per mole. So any molar mass less than 1 gram per mole is just absolutely impossible because you can't have partial atoms. So your molar masses should come out to be greater than 1. And for a gas, they're not going to be ginormous. They're probably going to be less than 100 or so. But, so if you got, 7 times 10 to the 15th, something went wrong. Any questions? Here's an example that's very similar to what we're going to do in lab on Wednesday. An organic chemist isolates a colorless liquid from a petroleum sample. She places the liquid in a pre-weighed flask and puts the flask in boiling water, which vaporizes the liquid and fills the flask with gas. She closes the flask and reweighs it. Her data is given below. Calculate the molar mass of the liquid. So the molar mass of the liquid and the molar mass of the gas are the same. Their densities are not the same. So we're going to do the same process that we did for that previous example. Molar mass is sometimes abbreviated MM. So that is the mass in grams divided by the amount in moles. So how do we figure out what the mass of the gas is? Is it 78.416? We need to do some subtracting. This is the flask and the gas. So this is not the mass of the gas. Here's the mass of just the flask. This is like if you've got a puppy who needs, worm medicine or something, and you have to look on the thing, how many tablets do I give him? It depends on how much he weighs. I don't know how much the puppy weighs. It's kind of important. So here, puppies stand in the bathroom scale. We have a puppy in our house. There's no way that puppy's going to stand on a bathroom scale, right? How do you weigh the puppy? You hold him, right? You get on the scale and you see how much you weigh, and then you think, I got to cut out the potato chips. And then you pick up the dog and you stand on the scale again and you weigh more now because you're holding the dog. And so you subtract and you get the mass of the puppy. I think pretty much everybody understands that, right? But then when we talk about flasks and chemicals, you'll lose your minds, okay? And you're going to take this number, you're going to take the mass of you and the puppy and give the dog way too much medicine and kill him, right? So don't let this flask and gas business mess with you. These are just things. So the flask is you are the flask, and the puppy is the gas. So we want the mass of just the puppy, so we're going to subtract 78.416 minus 77.834. So the gas itself only weighs 0.582 grams. And you can look at the words here, and the words are going to help you. If I have flask plus gas, and I just want gas, that means I have to subtract flask. So there's my mass. I can stick that in my equation way up at the top. 0.582 grams. Now I need to find moles. So I'm going to use the ideal gas law. When I rearrange it to solve for N, I get N equals PV over RT. We should be getting better with the units now and recognizing milliliters isn't going to work. I need liters, right? So milliliters on the bottom, liters on top. Liter is 1 times 10 to the minus 3. Milli is 1 times 10 to the minus 3. So this is 0.213 liters. 100.0 degrees Celsius. Our measured temperature here has 1 decimal place. So if I used the rounded version of the conversion factor, I would be losing some precision. So here I definitely want to use 273.15. And this is going to be 373.15 Kelvin. And then torr, I need to take atmospheres over 760 torr. Remember, torr in millimeters of mercury, are different names for exactly the same unit. So this is 0.99210 atmospheres. So I'm going to take these values now with their correct units and plug them into my equation. I didn't leave myself much room. Atmospheres, liters, kelvins. .9921 times 0.213 divided by 0.08206 divided by 373.15. Did you get that number? If you multiply without parentheses by 373, then you get off by a factor of 373 squared. Because instead of dividing by 373, you multiply and things get wrong, very wrong. It's important to remember that leading zeros are not considered to be significant figures. So we should not call the 6 the last significant figure because those leading zeros don't count. So there's my moles. I can plug that in up here. 0.006911 moles. I'm getting a number 84.334, which I will round 84.3. The units are grams per mole. Is that a reasonable molar mass? It's bigger than 1, and it's not ginormous, so it's possible. Any questions?